Okay, lastly, let's talk about describing correlation. That means to describe the relationship between two sets of data. So to begin, let's consider the following example. In a city, we sample 12 houses, and for each house, we get its size and its price. Okay, so basically, for each sample, we collect two values, two attributes. Okay, for each house, we collect size and the prices. For these 12 points, we can plot them in a scatter plot like this. Okay, and we have mentioned to you last time that if we have a scatter plot, that somehow tells us some relationship between the two variables. For example, here we seem to see a positive correlation. When a house gets larger, we somehow believe or tend to believe that the price will also go up. Of course, no one says this will always be true, okay? But it has that kind of tendency. So, graphs is helpful for us to get intuitions, but we also need some numbers that help us to decide the degree of correlation. So we want to measure or describe the correlation between two variables. Okay? Correlation will be defined precisely later, but basically we say correlation is a kind of linear relationship. Or we can say when two sets of variables have high correlation, then they can be better described with a linear equation. Okay, when one goes up, the other also goes up in a linear manner. If that's the case, then they have high correlation. Okay, so let's start to define something, some measurements to describe correlation. Suppose we have a set of paired data. That means for each data point, we collect two values, xi and yi. Okay, so we will have two sets of data, and x1 corresponds to y1, x2 corresponds to y1, etc. What we want is to see when one variable goes up, does the other one also tend to go up or down? We hope that by observing how by observing how one variable changes, we can somehow predict the other variable. Okay? Or more precisely, suppose xi is larger than mu x. Is it more likely for us to see yi be greater than mu y or yi be less than mu y? That's some question we want to answer. If one variable goes up, tend to make the other variable goes up, then when xi is above its average, we should also see yi above its average, right? Let's look at this by using the scatter plot with our previous example. If we plot mu x and mu y, we would get something like this. Okay, this is mu x and this is mu y. We can see that when x is above mu x, we tend to have y above mu y. When x is smaller than mu x, we tend to have y smaller than mu y. Okay, and this fits our intuition that they have positive correlation instead of negative correlation. So we hope that the measurement, the indicator we define can capture this characteristic. Okay, can give us for example, a large number when what happens here is true. Okay, we hope that our indicator will be large. If x greater than mu x implies y greater than mu y. So let's see how to do it. So basically, we rely on the product here. when xi is greater than mu x, if yi is also greater than mu y, then the product would be positive, right? Or if one is negative, then the other one would also be negative. Then the product would also be positive. On the other hand, if when one is positive, the other one is negative, the product would be negative, and that tend to give us a negative outcome, negative aggregate outcome. So based on this intuition, we define the covariance of a set of two-dimensional population data as this, sigma xy. For each data point I, we calculate the product of xi minus mu x times yi minus mu y. For all the products, we sum them up and take average. So that means if most of the data points are here or here, then we would have a large summation, okay, because most numbers are positive. If most data points are here or here, then we would have a negative summation. Then we say, well, we have a negative relationship, okay? If we are talking about sample data, then we use this notation SXY, and we are talking about a sample data, so the sample size is small n, and we have x bar, y bar as the sample mean, and the denominator would again be n minus 1. So let's use our example to show how to do the calculation more precisely. We know that we have our set of data xi here and yi here. These are the sizes of our houses, and these are the prices. First, we calculate sample mean and sample mean. How do we know that's a sample? Well, it's because in that problem, we collected the data from 12 houses. As long as in that particular city that you are interested in, there are more than 12 houses, then you know your data is a sample data set. For x and y, we calculate their sample mean. Then for each data point, we can derive the deviation from mean, right? Xi minus x bar and yi minus y bar. For each house, we can calculate these two numbers, and then we find their products. For this specific example, all the products are positive. That means when one value is greater than its mean, the other indeed is also greater than its mean, etc. Okay, and then we sum them up, and then divide it by 11. That's how we get our covariance, which is sample covariance. When you see that's positive, that basically tells you that, yeah, we have positive correlation, because overall, in an aggregate sense, the number is positive. Okay, if the covariance is negative, then we say the two variables are negatively correlated. But we still want to be able to decide whether they are highly positively correlated or mildly or slightly negative correlated. We want to know whether a given number, a given correlation measured by covariance, we want to know whether this number is considered large or small. Okay? How do we know whether 617 is large or small? We don't know. In particular, we don't know whether it's large or small because we don't know how the two variables themselves are dispersed. Okay? When you have two sets of data, if in each set you have a lot of variability, then you expect the covariance would also be large because that measures some kind of variability, right? So let's introduce another measurement that may also be very helpful. That measurement is correlation coefficients. To take away the auto variability of which variable itself, we define correlation coefficients for population and sample in this way. Basically, we take the covariance and divide it by the standard deviation in each set, So in our example, we are talking about sample correlation, and we can get the standard deviation for the sample standard deviation for each variable. Once we complete this division, we get 0.729 as our sample correlation coefficient for our example. Okay, rho and r are widely used for population and sample correlation coefficient. Mathematically, we can show that we always have rho and r, the correlation coefficient, to be within -1 and 1, which is very good, because then, depending on the magnitude of these numbers, we can somehow get a feeling about how strong the correlation is. Okay, as we mentioned, if a number is positive or negative, then we say there is a positive correlation or a negative correlation. If it's 0, there is no correlation. But when it is very close to 0, we tend to believe that there is also no correlation, right? So what's the standard? It's there. In practice, people often determine the degree of correlation based on the magnitude of your correlation coefficient. Basically, we use 0.25, 0.5, 0.75, and to be the 3 cutoff points. When your magnitude is within 0 and 1/4, we say it's a weak correlation. When it's between 1/4 and 1/2, we say it's a moderately weak correlation. Above it is moderately strong, and eventually we say it's strong. Okay, of course, these are just some typical rules. No one says that you need to follow this. It's just some rules that people in practice typically apply. Okay, but indeed, if you have a variable whose correlation coefficient is 0.254, you may also say that you believe that's a weak correlation. No one will say you are wrong. Okay, but so the criteria here are just some typical rules that you may take it as a reference. Lastly, I'd like to warn you one thing. Is the difference between correlation and independence. A correlation coefficient only measures how one variable linearly depends on the other variable. What does that mean? A correlation coefficient can only measure linear relationship. So if the two variables have strong linear relation, then you have large correlation coefficient. But if the two variables have a strong nonlinear relationship, your correlation coefficient cannot show it. For example, here, suppose you have a few data points, okay, 1, 1, 2, 1, 3, 1, 4, 1, blah blah blah, up to 10, 1, and then 10, 2, 10, 3, 10, 4, 10, 5, up to 10, 10. For these 19 points, if you really calculate their correlation coefficient, it's just around 60%. Okay, but you obviously will not say that the two variables are having a strong linear relationship, right? They have some relation. You won't say they are independent. So one variable obviously affect the other variable, but as long as it's not in a linear way, your correlation coefficient does not mean a lot to you. Also, in this even more extreme example, you have data points 1, 1, 2, 2, 3, 3, 4, 4, blah, 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 up to 10, 10. And then 11, 9, 12, 8, blah, blah, up to 19, 1. When you have this, and if you really calculate the correlation coefficient, it would be 0. It would be 0. You may want to try it at home, but indeed you will get 0. So what does that mean? So that means when you have two variables and they have a strong nonlinear relationship, you probably cannot see it with your correlation coefficient. Okay? If you have strong linear relationship, your correlation coefficient will tell you that. But for nonlinear relationship, correlation coefficient is just not so helpful. Okay? So the final conclusion is that being uncorrelated, like here, being uncorrelated does not mean being independent. Independent means one variable simply has no relationship with the other variable. Okay? Uncorrelated just means there is no linear relationship, but there can be something else. There can be something else. So correlation and independence, they are different things. Okay, that's the end of this week's video. Thank you.